So good afternoon, everyone, and welcome back from lunch. Today we are excited. In fact, we're overjoyed to share with you some of the transformational work we're doing in terms of engineering at Schlumberger. Specifically, we will share how we're using aPriori and some other CAE tools, combining them with multidisciplinary design optimization platforms to enable some insightful trade-offs right during the engineering phase of our product design. So I'll hand over to Laurent to go over the outline. Yep.
Thanks, Ryosa. So quick outline. So we'll look at the introduction first. Executive summary, we'll go through 2 slides just to really get our points across. Then we look at why design trade-offs are so important when we work with teams. And then we look at what are the limitations we see with current or historical design trade-off. And then I'll hand up the buttons to Ryosa for the interacting design trade-off and how production digitization is enabling us to do those interactive design trade-off. And I'll take on the summary and the conclusion again. So Schlumberger, we work with Schlumberger. We work at Schlumberger. Schlumberger is the world-leading oilfield services provider. It is a technology innovator. It has more than 100,000 people worldwide. We are a very diverse and very well-skilled pool of talent. We have 140 nationalities in Schlumberger, working in 120 countries. We really deliver product and services. We do both of those activities. Our revenue last year was $33 billion. And we are known to be innovative people. And for Schlumberger, we believe that innovation happens when people, visionary people, dare to try. And it's a little bit what we're going to show you today. So we're going to talk about multidisciplinary design optimization. It's a big, long word, but what it means is you take your CAD, your software, CAD, which you use traditionally to do all your hardware pieces. Then we're going to combine that with your finite element analysis model. Pick the one you prefer. And then we combine all that with aPriori for cost modeling. Eventually, what we get is an optimized cost, and that's what we're going to share with you. So executive summary. We have 2 ways of looking at design trade-off. First, it's one that we're going to call static post-design trade-off. What it means is we've done a lot of work, and then we combine it and we show it to our stakeholder, or client, or suppliers. Here, I'm going to show you an example of what we've done in the past with that product here. So if you look this on the picture, you can see a subsea landing string. It's a safety mechanism used below a platform in the ocean. It's a very big piece of equipment. If you can see, not Waldo, but there is 2 technicians there. It shows you the scale of that tool. It's about 4 to 5 stories tall. So as a team, we had to develop the next generation of this product. And as we've seen earlier with previous presentation, it's good to very early on as many concepts as possible. So here we developed 7 different concepts, and we did a lot of FEA work, a lot of testing, a lot of hardware testing. But including to all that work, we run about 7,000 quotations with aPriori to get the price point. So when you do a trade-off, when you share trade-off information with your stakeholder, your management team, you look at different charts. So a classical one is a spider web chart. And here, I put the best price as the top one at 12 o'clock. And then when you go around those 8 axes, you have the tool internal diameter, the tool external diameter, outside diameter, and you can go across. What's interesting to do the design trade-off is to map each of these concepts with their respective criteria. And so here you see for concept A, that's the shape or area it took. Then we look at design B, design C. That was the one we really like as a technical team. It has all the bells and whistles of a Ferrari. For technical people, we love it. But if you look at the best price, it's ranked in a 0 to 5 scale. Maybe it wasn't the best price. Then we go on, D, E, F actually had a better price. But for us, it was not the Ferrari. It was maybe another brand, I won't say any. But it had all the functionality we needed, but it was not our strong interest. And then we had G. So what was interesting here, with aPriori point of view, is very early on, we were able to have price points and being able to select which design we went to. And we decided to take F and improve it, of course. The one we really like as technical people was the Ferrari in red at $1.5 million. And the one that was a bit more aligned with what the market is able to buy was the F1, the sixth one. But that's static post-design trade-off. Now we can look at a bit more what we're going to present today, and we'll go more into detail. It's really an interactive upfront design trade-off. It's a bit of a complex graph. We're going to see more of the detail, and we'll see it in dynamic fashion a bit after. But what you have is parallel information on this graph here. And what it shows on the right-hand side, on the left-hand side, is there are the inputs. So the first 3 lines here are input. And on the right-hand side of the graph, you have design output. And you can change the variability of each of those parameters to get your output. To put it short, to understand what was going on here, we had a cylinder that was a piston, which is loaded with a complex loads pattern, which is in buckling mode, and as well you have collapse pressure. And what we had as a story is we had a 10,000 PSI piston, and then one of our clients said, hey, I have an application where it's 12,000 PSI, the envelope that I need. And what we do is like, let's go and check if it works. It didn't work. It was too marginal as a design. So if you have engineers in sustaining, we know the trick. We say, hey, let's take a higher grade material in canal 718. And what we see is that our baseline price of 126 with the original design, when we take in canal 718, turns into to be a $345 solution. Fantastic, we have a solution. But thanks to some of this interactive upfront design, we were able to find alternate designs with different materials, different geometry, different size, in which we found a price point at $147 solution. So for $20 more, we had a solution instead of 3 times the price. So why do we need design trade-off? So it's very important. We talked a lot about collaboration today. So design trade-off are used to communicate. So it's a communication tool between the different stakeholders in the value chain of your team, your supplier, your management, your technical team, your risk assessment team, your financial team. It's a visualization tool in order to simplify what's typically complex. Typically, you have aggregated data. They are often technical, but you can have financial data as well, other type of data. It's always good, if you can, to have the previous generation of a tool or a point of reference that people can relate to. Here, as an example, it's from an architectural example. I purposely took it far away from our domain. We see a team of architects that looked at 12 alternate designs. Then they look at 4 different criteria. And when you have that information, you can then do a performance analysis. You combine those criteria together. And then you have a ranking from, let's say, 0% to 100%. And then you are able to rank that. And so in this example, we see that the alternative 6, 10, and 12 were the best design that team was supposed to work on. In order to expedite generation of trade-off, we get some benefits when we are able to do that. So we will look at expediting trade-off. But when we're able to do that, we can have more innovative ideas because we can do some sensitivity analysis around some of the points we look at. We can as well accelerate the project because now we take, as a team, the decision a bit earlier to go in that route or that route as early as possible. Then we can select the cost of the tool or the cost of the building. That's the cheapest. So overall, you save in labor and spend on your project. All that maximizes return. So what's the limitation of trade-off curve? What do we see? So here, for example, we see a very good example of a great work of trade-off curve, but that has limitation. A team of engineers looked at 6 different concepts of airplanes, and I'm sure each one of the engineers that was behind each of these concepts loved their airplane and fight for it. But it's very interesting to see that, for example, the fifth airplane has a certain cost. I think it's $400,000. But its performance, which is on the y-axis, you have the performance. Its performance is less than another airplane, the patent design, which is at $300K. And so what's interesting, if you ask each of these engineers, for sure they tell you they have the best design. But what would be interesting is to discover or to look for this red line here, which is for a certain price point. If you go up, try to find for a certain price point the best optimum design that you invest. So if you're in the business of making cheap airplane, $200,000, do you want, or $250,000, do you want to have a design that's 40% performance, or do you want one that's potentially is as good as 80%? Okay? So the name of the game and what we're going to show you is to look for this optimum. If we look at literature, you can go to Wikipedia, the source of literature. This is called the Pareto front. So all the game here is to try to optimize different objectives. So objective 1 on the x-axis, let's say it's the weight of an airplane. We're going to try to minimize the weight. And then objective 2, it's the cost of this airplane. So we're going to try to minimize that. What we see on the top right-hand corner in green bubble, there are all the potential design space of solutions that exist. And then what we see below this red line, the Pareto front, are utopian or non-feasible design. You cannot have an airplane that weighs nothing and costs nothing. It has no functionality. Okay? So the remaining of the slides are going to be to look for potentially some Pareto points, some of those optimum points that are on this line. And that's where I hand off to Uyosa.
Thank you, Laurent. So like Laurent mentioned, the interactive trade-off that we're now looking into and we're now working with is enabled by what we've termed product digitalization. So before I go in and share the results on this, I would like to first define what product digitalization is. We've defined the term product digitalization as the use of digital technologies to transform our engineering design processes and workflow. In the wake of digital transformation, as you can hear, as you've heard from the beginning of this session today, digital transformation significantly reduces the cost of product engineering. So for us as engineers, within the product development aspect, we're looking at how can we transform our product design workflow. And the type of transformation I'm talking about that I'm focusing on in this talk is automation. How can we automate our product design workflow? This automation, we've identified 4 key drivers that enables us to be able to implement this automation. The first one is model-driven engineering, which is, in fact, rapidly growing and I think is very near to maturity today. Most of us here would agree with me, 10 years ago, you were not doing as much of modeling during your product design as you are doing today. So that growth in change, in adoption of modeling and simulation as an engineering tool is one of the enablers for what we've termed product digitalization. The second enabler is discretization, democratization, a lot of big words, but democratization of these modeling tools. So my first engineering job, I was an intern, and I sat next to a group of 3 individuals working for this global company, a global manufacturer of mining equipment. And it was 3 guys, and all they did all day was run FEA. Okay? No one else in the company did it. They only did it, and that's all they did. But moving to where we are today, all the engineers in the product teams can run their FEAs, right? And not just run FEAs just for beautiful colors, but run it with actual integrity. So that's what is called democratization, where you take the tool now and multiple people, a lot of people can use it. The third enabler is the digitalization platform itself. It's a platform that would allow us to do this engineering workflow automation. We found this solution to come from multidisciplinary design optimization softwares. These are softwares that over the years have grown and evolved to be able to run optimization using any tool. If you're running ANSYS, they can connect to ANSYS and do your optimization. If you're running Abacus, they connect to it. You run in Excel, they connect to it. So these softwares have evolved to be able to connect to our various engineering tools. And now with that connectivity, we're going to use them to enable workflow automation. The last enabler for product digitalization here is the simulation process and data management, SPDM. So all the data that we're generating from modeling and simulation, the ability to store those data, the ability to retrieve them, the ability to manipulate them, and use them to drive business decisions. So in the next few slides, I'm going to give you outline 3 steps that we've taken to enable workflow automation, and then finally a dynamic trade-off curve using aPriori. All right, so the first step is model-driven engineering. Like I said, it's an enabler. So how does this come into play? The picture you see on the right of your screen is a library of all the models that we developed during the project that Laurent mentioned earlier. Some of these models were developed during the concept identification stage, where we're evaluating different concepts and identifying which one is best. During the product design phase, where we're looking at design requirements and ensuring that our design actually meets the requirement. The example here is a ball seal, where we're ensuring that, yes, the ball can seal the pressure we're designing for and the temperature we're designing for. The third, looking still within our product design lifecycle, is design optimization. You've identified your design, now you need to optimize it. And the example here is using aPriori for design for cost, where we've already identified the best solution that we want to move on with, and then now we feed this through aPriori and do iterations to optimize for cost. The next source of engineering models that we're going to use to enable product digitalization comes from the product validation step, where we are actually taking our design and running all the environmental variables through our design to make sure that our design is robust enough to actually go to the field. And finally, when it goes to the field and we have failures, we use modeling and simulation to evaluate our failures, right? So effectively, this is how we develop all the models that we use to address the functional requirement of a product. You put all these models together, it gives you a library of product. That's the first step. The second step is to then take all this model and create an automated engineering design workflow. And I'm going to walk you through a simple one where we don't go into elaborate detail here for the sake of time. So take, for example, I have to design a part, and this is a true case, a case that we looked at and we created a workflow for it. I have an existing part, and the client comes to me and say, can you update this design? Can you increase the performance to meet our requirement? They give me their requirement. They give me some dimensional requirement or some load requirement. I feed that through MATCAD, right? Because I already have a MATCAD calculation for this product. I get my safety factors. If my safety factors are not met, what you don't see here is that there is an automated loop that goes through and modifies those dimensions until my safety factors are met. If they cannot be met within the range of variations, it's going to check out. That's why you see false there, it checks out. It's not feasible. But if I find a feasible design, then I go on and create the CAD model. I take the CAD model into aPriori, get my cost implication, and then I finally took all those models and I run FEA on it just to validate my design, looking at my environmental variables. So effectively, when I run this, what do I get? I get all my engineering files. My calculation package is automatically generated. My CAD drawings, my CAD model, my analysis report is generated. That's the second step. The third step now, using this workflow, right, still within the same MDO platform, we go ahead and we look at all the variation. For this specific instance, we looked at the variation of designs we've had over the last 2 years from our customers. The variation of environmental conditions, load conditions we've received over the last 2 years from our customers. We use this to create a robust DOE space. So each data point there is a potential design, is a design on its own with the dimensions and the client information. And then using the automated engineering workflow, we execute each of these designs, and we effectively design it automatically. Guess what? I didn't mention earlier, the workflow we generated typically takes us 2 weeks of engineering time. It went from 2 weeks to 6 minutes. 6 minutes. So now, looking at hundreds of designs, I can execute this overnight, come back, and this is a real case, and then be able to do the exciting dynamic trade-off that Laurent talked about. It's very important for me to mention here that the software we're using to do this is Mode Frontier that's provided by Estico. So if I go in, I've generated a lot of engineering that addresses each of these individual design. Now I get my result. It's a dynamic chart, as you're going to see in a minute. And I'm going to have an interactive session with Laurent and say, well, this is my chart of my design. I don't have a single design anymore. I have tons of design. Each line you see there is a unique design, where the first 3 columns, the first 4, I have material ID, OD, length, and the material index. And then the last 3 are the capacity of the design, the FAT capacity, the tensile capacity, and the cost. Those are outputs. So I have pretty much explored the use case of this product, and I'm going to ask Laurent, what would you like to have for your client use? Assuming he's my client.
We just got a call from Malaysia,
okay.
And we have a rapid response to respond to fairly quickly.
Okay.
And they're interested to have a latch mandrel, which has an ID of 6.4
okay.
for drift. The tensile load is £500,000,
okay.
And then they're looking for like 19,000 psi of pressure.
Okay.
I cannot read your graph. Do we have any solution?
Okay, let's assume you don't even see my graph, okay? Typically, I get something like that, and I spend 2 weeks of engineering time to give feedback and say, this is the potential cost, this is what it looks like, or maybe it's not even feasible. And then the conversation goes on. But right now, I can actually go on this chart, and I can move my ID to what he has asked for, 6.4, and the designs that don't meet that requirement are grayed out. I can go into my tensile capacity. He wanted a capacity of 500,000 pounds. I simply drag that up as well, right? Set the limit to 5,000 pounds. Designs that don't meet that requirement are phased out. And then he wanted a pressure of 19,000 psi. I drag that up as well. Designs that don't meet that requirement are phased out. Finally, I have all the designs that meet his requirement. Within this, I can do trade-off and identify the cheapest design that meets his requirements.
Not cheap enough. There's competition in Malaysia. It needs to be less than $7,000, if not we're out of the market.
Okay, so that's the conversation we should have had in 2 weeks. But I can do that on the fly as well. I reset. Now you want $7,000. Let me see what I can get you for $7,000. Great. I can give you 500,000 pounds. I can see there on my tensile capacity.
Good.
For my pressure capacity, that's the second to the last one. I'm just shy of what you asked for, 19,000. I'm 18,700.
I can talk the client into it.
So that's good. So we're fine. Is this good for you?
But there was a drift. You remember we had a drift of 6.4.
Oh, okay.
They need to run the tool within the tool.
Okay, so effectively we have another critical requirement. So I'm going to just simply go there and drag that to 6.4. And do I still have a design for him? Yes, I do. I still have a design, and the final design is the cheapest one I can get you on my data point there is $6,650. It meets your requirement.
So I can say, Malaysia, we found the Pareto point, $6,650.
Yes.
We've seen innovation, collaboration, and acceleration.
Absolutely. So this is what we're doing today. It's transformative, it's reducing cost, it's reducing time, and the impact on engineering and the future of Industry 4.0 is huge. I'll let Laurent give us a summary of the talk.
So quickly, we've seen that static post-design trade-off are good to capture knowledge, but they tend to be a bit late. Whereas interactive design, upfront design, really help to find and poke and look for an infinite space of alternatives. As well, we've seen that we could find optimum concept on the Pareto front and select one Pareto point. And then most of it, the biggest value, that's what we've heard many times today, it's to energize the communication, energize the discussion of what-if scenario among the different persons along the value chain. For product digitization, which include cost modeling like aPriori, we can really start talking with like business comparisons among the different concepts with a price point. From your stakeholder to have a trusted information, it's better to have a known reference. It always helps in the discussion. And we've seen as well that we can accelerate all the different points along the life cycle, whether it's for customization of design or increasing of the family sizes, or sustaining, or even knowledge capture, knowledge sharing. If you have this algorithm, this DNA of your family of tools, and you have a new employee come in, they can very quickly work with what the previous team has left. So overall, what we've seen already many times today is within the faster market that we live in, improved and accelerated decision-making is really the key to be dominant and even sometimes maybe survive. So I will let you with a few conclusion points. So we've seen how we can combine CAD, FEA, aPriori, or many other softwares in order to optimize different aspects, but the cost being one of the primary drivers of business. Always question and challenge the assumptions. I'm sure all of us, we believe we have the best product, but I'm not sure we all have the most optimized product. I'm not sure all products are Pareto point products. It's very important to democratize digitalization within your teams, within your work, to make sure that we can find those Pareto points. As I mentioned before, calibrate your scenarios. That's how you'll get trust from people. Then only negotiate the what-ifs with the different people across your value chain. Tools like this allow you to measure what's important and not what's easy to measure. For example, fatigue in some application is critical to know. Fatigue is very hard to measure. When you have a digital twin of your tools, you can measure fatigue. And finally, as the last point, I will say that communication is key to use this trade-off to make things more understandable and not more complex. Thank you so much.